And we are live.
Live, yeah.
StreamYard says, now let's see if we are indeed live. And it seems we are live on Twitch. And I'm guessing we are live on YouTube
Live.
also. Let's mute this. Good evening, everybody. Welcome to the stream. My name is Yannick. I'm the French guy from Switzerland. And this is a community stream on the Ubuntu on Air channel. Um, as you can see, Andrea is back because we are going to go to I say we, Andrea is going to go
We,
through
we.
phase 3. It's like the Marvel universe. We're on phase 3 now. So
Yeah, more episodes. It. I thought it was
yes,
just like one episode one, and then we did episode two. Now episode
and then
three.
episode 3. Yeah, it's a trilogy.
Trilogy.
Everything needs to be a trilogy, otherwise
Yeah,
it's
at least.
not
Yeah,
working.
yeah, I agree.
So we're going to keep on um, doing what we did previously. That's program a microkernel. And again, I say we, but I'm not doing a lot. But just to recap, if you haven't watched part 1 and 2, so we started by writing a small bootloader. Then we ditched that because we're going to use grub instead. And then, Andrea, you wrote a very basic kernel that I think it said hello or something like that
Yeah, there was the
in the
Hello World.
beginning. Yeah, the hello world kernel. Then you extended that to print stuff with a blinking cursor and moving next line and stuff like that. Then last time, 2 weeks ago, we did what you did a how did you call that? A
Voluntarily preemption model.
voluntary
Mean
preemption model. So that
there are
that's two
tasks,
threads. Yeah,
threads,
two threads, and one thread executes some code and then yields control to the other voluntarily. Right.
that's
That's where we were
yeah.
last time.
We don't have a
So
scheduler because we were switching directly, like the task had to point and call explicitly the other task that
yes,
was
yes.
going and taking the CPU.
So what are we going
So,
to do tonight?
yeah, so I thought it was interesting to see and extend this concept, like resume from last time, and instead of like the task being like instead of the task calling directly the next task, it would be nice to have a scheduler. Like in our kernel, there should be a subsystem that decides the next task that is going to take the CPU when someone heals and releases the CPU. So yeah, we are going
So
to do that.
okay, so to be clear, so the scheduler will decide when it's time for one task to stop doing what it does and switch to another one. Is that correct?
That's yes, that's in a
In a
general
nutshell.
purpose
Yeah.
kernel. Yes, and this is what we are going to do probably in episode 4 at this point. Uh,
Okay.
right now, this scheduler. What I would like to do today is to have a scheduler that decides the next task. The concept
Okay.
of time slot, like having a periodic, we need a periodic source of interrupt to implement like a concept of time slot.
Okay.
And for that, we need to implement the interrupt manager. And this is like there's a lot to do. It's probably a full episode to implement that. The close step, the step that we can do in one today, is to like implement a simple round robin scheduler, for example. So I can imagine we can do a list of tasks, and the scheduler, when the kernel calls the scheduler, it will simply select the next item in the list. Or maybe we can see that as a like the first item in the list will be popped out of the list and will take the CPU. And when when it voluntarily releases the CPU, it will be added back to the bottom of the queue. So it would be a simple round robin queue. Well, more than a round robin, it's more like a first in, first out.
Okay.
Except that task will not die they will release the CPU, and they will
Okay.
be added to the bot.
Good.
That's the
Good.
idea, more or less. We're going
Right.
to improvise, of course, as usual.
And so, because we don't have P threads, we don't have standard library to support that, so we're gonna have to write everything. Are you?
We don't even
Are
have
you?
lists.
Yeah. So you're going to rely on the hardware to call periodically the scheduler, or how is that gonna work?
No, the scheduler will be still called by the tasks directly. So we're still
Okay.
using a voluntary preemption model.
All right. Okay.
And with the difference that, if you remember, like, let's see, let's open
Let's put the screen on. Oops.
Yes.
Yeah, there we go.
So in to recap from last time, I'm just going straight to the scheduler code. The task we're calling switch to. You see it. So this one was saying switch to init task from myself, that is T1, and the init task was doing switch to T1, and I am init task.
Okay.
What I would like to do is to do just schedule something like that.
So
that
tasks
is what
don't have to know each other's. No.
Exactly. Tasks don't have to know each other. So I can have 2 tasks or 10 tasks or 10,000 tasks. I just call schedule.
Gotcha.
And that's it.
Okay.
So yeah, we can start. Let's see. I just noticed something that I don't like. As usual, this is for those that didn't watch the previous episodes. This is like live coding and improvising. So I will probably notice some bugs or stuff like that. This is not a bug, but defining null as 0, I think it would be better to define null as something like this, because I may want to use null with pointers. So okay, that's not a bug. It's just a.
So you're basically opening the door for null pointers exceptions.
Exactly. I can.
Because
Yeah, that's something interesting. We can. So because in this is an anticipation maybe for next time in Intel, there's not a big difference between interrupts and exceptions. They're actually managed in by the same, let's say, hardware subsystem. So it's interesting to have like null so that we can trigger exceptions, but right now we can't, because we didn't program the interrupt controller. So if we trigger a null pointer, the reference, for example, we would just reboot the system, because the exception would try to call the exception handler that is not defined. So it will trigger what is called a double exception that is totally acceptable. The double exception will try to call the double exception handler that doesn't exist. So there would be a triple exception, and in hardware, the triple exception will result in a reboot. So that's by hardware specifications. So right now we have an easy way to do a very fast reboot by doing something wrong. Okay, so what I would like to do is a little bit of refactoring, because like these types, I would like to split this main into multiple files, because we have a main that contains like some definitions right here, everything, console driver and the scheduler. And
that's a monolithic kernel.
That's very monolithic, but it's fine to have a monolithic kernel, but not a monolithic source code. That's bad. So for example, let's move this into a .h, I would say. Like you can do types.h, for example. And usually I do this, types h I. Well, Linux does this, and I like that.
Except it's if and if, probably.
If def, define.
If and def.
Yes. Oh, yeah, you're right. If not defined, exactly. Thank you, Jan. And then, yeah, that's because like if I include this .h multiple times, it will only be actually defined one time. So that's the only reason.
Standard C best practices.
Yeah, it's C best practices, nothing to do with kernel programming. This is just right. Okay, cool. And in main, now I can do like an include types.h. Except that we also need to change the make file, I guess, because we are not exactly. We're missing something like this, dash include dot. Because otherwise I would have to, do something like this. And I compare I don't know, this is probably just cosmetic or C best practices programming. I don't know, but it looks better like this.
Yes.
Especially if we want to move around .h files into multiple locations or subdirectories, this is better. Okay, so now let's see if I broke anything. No, it's still compiling. Okay, console driver, I may want to do the same. Like, for example, move like all the defines up here. And yeah, I guess just that in a .h, console.h. I'm doing this even if it looks like boring and refactoring, but I want to have like the scheduler self-contained without any other things. So
yeah,
console.
It's better to do that now than
I could have done this offline, but the purpose of this series is to like code together. So so I think it's good to
perfectly fine.
What am I missing? Sorry?
Nothing. I said it's perfectly fine.
Oh, it's perfect. Oh, sorry. I thought you said that you're missing something. Console H. Cool. All right. So right here, include console H. And this one will go into a separate .c maybe. So, okay. This one, oh, this is also something that should go into console H. Address port with head colors. And this is another thing that, let me move this up here maybe. Because that's generic enough. Usually this goes in something that is io.h. So we can do this io.h.
So our Pasta OS will be Linux compatible.
Yeah, and I'll show you why I'm doing this, because we're gonna take a little piece of Linux. So at least I don't know if that works, but I had in my head the list, because we need lists and we don't have.
Yes.
We can either implement lists from scratch or take the code from Linux that is GPL, and our code is GPL, so it's totally compatible with from a license perspective. Okay. O.h. I guess we need to include types here because we are using UE in 16. And the same probably in console H.
And again, for those who didn't follow previously, we don't have any standard C library or includes or anything. So that's why you had to define those types for this kernel. Yeah.
Yes. Okay, cool. This is going to be console.c, I guess. Console.c. Include console, yes. And print k is the public interface print k, so it's going into the .h.
Yeah.
Perfect. Main, what we have? We just have the scheduler. Let's see if it's still compiling.
It won't because you forgot the
Yes, good. Include.
And the makefile, you need to compile console.c from the makefile.
You're right. You are totally right. See, we are doing together.
Yeah.
I told you.
That's what pair programming is about.
Yeah. Let's do a make clean to make sure. Okay,
Yeah.
cool.
Good.
Now I just want to move. This should go. Where are we using page size? Oh, for stack size here. Okay, let's put this in a sched.c, for example. Actually, this goes in sched.h because we have a struct definition. Yeah. So let me see. Do we have anything else that would go? No. Okay. You can move this in sched.h, and as usual, if def sched.h define sched.h and div sched.h. Okay. And this goes into sched.c. Include sched.h. Are we doing any print k here? No. I guess we need to include, well, we need to include types, but I can include types in here. All right. Sched. What we need is to define switch2 as a public interface. So sched.c. This doesn't need to be static because we want to use this from the external also. All right. Oh, we need to change the make file to add also sched. Let's see what we have. In task, okay, init task is also need to be public. And no, init task init, sorry. Also init task, because it's defined, we are using this from main. So sched.h extern init task, and task init also needs to be like a public interface. Let's see how many errors we get. Static. Oh, yes, because of course. No, wait. Static in main. Oh, we have a. Okay. Yes. Wait. Of course, we don't need that. We need that. Cool. All right. Cool. Let's see if it's still working after this big refactoring. It's still working. Okay, so we have many things now. A lot of files. It
begins to look like a kernel.
It seems like a real kernel, yes.
Yeah.
Let's do just code refactoring, because we didn't change anything, not a single thing. It's just we just have a better looking code, that everything is properly logically separated.
Yeah.
So yeah. And by the way, in chat, if you have questions, feel free to ask. Yeah. I'm not looking at the chat, so Yannick, if you see something.
I'm looking at the.
Because I have the chat there, and my screen is there. I can even cross my eyes, but that's not ideal. All right.
Hello to everybody in the chat. I see multiple people. Welcome to part 3 of our microkernel adventures.
Yes. All right, so scheduler. Let's try to model a proper scheduler rather than relying on context switching directly. What I would like to do, first of all, is I would define some task or thread states. Actually, let's use task. I know that if this is even in the Linux kernel, sometimes they're using task, other times threads, but usually they're kernel threads, but they're called tasks. So I would stick with the same terminology that is used in Linux, even if it's not 100% correct. And I think it's not that it's incorrect. It's the task struct is used in Linux to represent both kernel threads and user space tasks. So I guess they're just using task in general.
Okay.
They should have used process, but we're going to stick with close as possible
Yes.
to Linux because we want to be able at some point to just import code from Linux. That would be
so we have two different standard names. So let's invent a third standard name to standardize everything. Yeah.
Exactly.
Yeah.
That's
That
a
always
good
works.
joke. Exactly. So let's use task. So therefore, there's going to be task states. I don't know how many states we will need, but right now there will be for sure task running. And I'm going to create task sleeping. I'm assuming we will need these two at least. It's going to be probably also task zombie, maybe, and potentially also TaskInit. But we don't have very much to do. Like we have a function that already initializes everything in the task. Usually you have a task init when there's a partial initialization, but we don't have anything like that right now. So that's not going to be a state that we are going to use. Zombie is probably, we will need that when we will implement a kind of garbage collector or something. When a task dies and exits, we need to clean up the resources of the task. So that would go into a zombie state, and the kernel will take care of releasing the resources allocated by the task. But we don't even have a memory allocator. So I guess this is what we need for now. We will see.
Yeah.
So we need, considering that we have task states, we need a state here in task struct. And when we initialize the task in sched.c task init, we are going to do task state. I would create the task as task sleeping, I would say, because like the task is not running yet. It's created and it's just sleeping somewhere.
So that's the, in C you would do a thread.start or something like that. Well, in C, C++ or thread start.
Yeah.
You're using pthread.
With pthread, well, because I was thinking pthread create, but pthread create also starts the task, if I remember correctly.
Oh, okay. I thought
this is more like, yeah, it's a create without running yet.
Okay.
Because we run when we do a switch too, when we do a context switch.
Okay.
Or when we will do a schedule soon, assuming we can implement a working scheduler. Okay, let's see. That's like very small change, still compiled, so we're happy. Now, what we need to do when we create a task, yes, it's initialize the state, but I need to put the task also in a list because I need to keep track of the tasks that I create and those that are running and stuff like that. So right now, I would just create I would just do like I would program this in Linux. So in Linux, I would do like struct list add next. So inside the structure, each task points to the next task. So I'm using the task struct to store the pointer to the next item in the list.
So it's a
And
linked list.
it's a linked list, yes. In Linux, this is actually a doubly linked, how do you say, double linked list, basically. There's a link forward and backward. So you can go in one way or the other with no cost, basically. It's actually big O of 1. And we need to implement, to include something that will be called list.h that we don't have yet. And so we're gonna get this list.h. We're gonna steal the code from Linux. List.h should be here. Yes. Fine. Now, that's it. That there's so many things here. We need. We probably need a little bit of a translation layer because we don't have all these includes. But look at that. We have Linux types. Ours will be types.
Right.
And we don't have these. So we're just going to remove that. Linux list. Let's just use list.h. That is our way. Okay. And first of all, coding style is important. So we're going to uniform this to our coding style. Oh, there's also something that I don't like here. There's a space. This is not. Should send a patch to Linux to fix this. Remove the blank space that goes against the coding style. No blank space at the end of line. Anyway. Let's see. TaskList. This should be pretty much self-contained because there's no no, how do you say, no memory allocation. And yeah, like list poison, I don't think we have that. But let's say we don't. Okay, we're gonna remove the stuff that we don't need. So the list poisoning is done. Okay, we can actually define those. Why not? List poison. Should we go in Linux and see what those are? List poison 1. Okay, it's doing something totally crazy. There's a point.
Kernel, what did you expect?
Yeah, because there's I remember now. There's a poison pointer delta that can be also randomized. But look at that. We're gonna copy this actually. Oh wait, where am I? List. Oh, because I source Linux. List.h. We're gonna copy that and let's say actually let's do this. Define 0.
Okay.
So we have the same code that is in Linux basically so far. So we know these are just magic numbers to determine when, like, if you're going to check if an item has been removed from a list, we can check if the pointers next or prev contains the special list poison values. That's the idea.
Okay.
We don't have true and false. So in our types, we're going to define type def. Actually, no, let me see. How is it defined in Linux? True. Cool. Awesome. You can just copy. Oh, look at that. The null is defined.
There you go.
Like we did. Oh, we did a good job then.
Yeah.
It's interesting that it's doing undef null, just in case it's defined somewhere else. It's gonna
just in case someone defined that as pure 0.
Yeah, exactly. Exactly. List.h. Oh no, need to go here. Actually, no, this goes in types.
Okay, so that's because we didn't even have true and false, or was
yes.
it? Yeah, okay.
Yes, because true and false are not not defined. As you can see in Linux is also defining that, because usually I think they're defined in stdef.h, something like that. We have
It's amazing the stuff we take for granted, like true false. That it seems like it would be defined by default as being 1 and 0, but no, it's not.
No, but this is why I wanted to do the scheduler also, because importing the list is like it's an easy piece to import from Linux, and we're actually doing a porting of Linux list in our past OS. That's amazing, and we can see, like, as you were saying, the things that we take for granted, they're not like that. There's a lot. Okay, so let's just do a quick review, then we compile and we try to see what breaks. Like, we don't have write once. For this, I think okay, I have an easier implementation of this that we can just copy. But let me see, because these are okay, they're basically writes and reads that goes in, that are implemented as pre-processing macros, and the purpose is to have a kind of guaranteed atomicity in the operation, even if there's no locks. But this is guaranteed to be like an atomic operation by doing some either GCC built-in tricks or architecture tricks. So we're missing this one.
I like the option of GCC intern tricks.
Because
it's not enough to know GCC. You have to be a GCC guru to know all the tricks and
this one, okay, it's interesting because I did a talk about memory barriers, and these are like implemented as memory barriers, and I remember this one, and this is basically let's do this right now. Like, we can define write once.
Sorry says hi.
Oh, sorry, UK. Hello, how are you doing? Thank you for showing up here in this. Yeah, I'm doing something different now than usual.
Yeah, it's not a violin.
Not violin. Yes, it's programming. Well, that's not too different than music. It's very similar, I would say. It's still, using a language, certain rules. So it's still like music.
We need to implement in this kernel. We need to implement a function that will use the internal buzzer of the PC to make it buzz at different frequencies to make music.
Yeah, that's a good driver to do. Wow, that could be one of another episode. Yes.
Yeah.
Okay, so this one.
Ave Mario then.
Okay, I will just implement this and then we comment the code. And I can. Okay, we need to do. Let me see if I remember. Volatile type of x is the variable. Has to be a pointer. Address of the variable. I don't know. That's probably wrong, but well. And then we do while 0. And this is going to get all these nice little preprocessor things. All right, so this do while is to be able to add this wherever I want in the code. So just ignore that. It's just ignore do and while. It's just this instruction right here. What I'm doing is saying this variable x. I'm declaring a pointer with the type. The type is the type of the variable, and I'm saying volatile because if it's volatile, the compiler will assume that this thing can be changed externally from this code. And what it's doing, it's not taking any initiative, like reordering instructions.
Okay.
You put this instruction like right here, the compiler is not going to do this.
Okay.
Because if it does this, look at what it's doing. It's like before it's updating the like the previous pointer, and then it's doing with the next, and I need to preserve the order here. So I want to preserve the order, and to preserve the order of the write. The write needs to happen. This write needs to happen before this other one. So I need to use.
You're temporarily suspending any optimization the compiler could do.
But only for this.
Yeah, only for this line.
For
Okay.
these 2 lines.
Okay.
And I could disable optimizations everywhere and not having to worry about this, or I can just be more efficient and restrict the like known optimizations to the single instruction that I want. So that's like there's also the counterpart that we probably need. It's read once. We also need that. So let's define also that. This is easier. It's like, well, we can do the do while. Maybe we can do this in one without the do while, because it's not an instruction, it's a read. So we can do vol type of x pointer. There are gonna be so many errors, but let's see. And the cool thing is that the cool thing is that it can be const. So this is just it's the counterpart of this, but I need the do while because this one is an instruction and this one is a value. You see the difference? So anyway, that's boring stuff. This is just to deal with the compiler. So, and keep in mind that this is C, that is considered like one of the languages that is closest to the hardware. So when there are people that are like, why the kernel is not written in C++ or in Python or in Rust? Like there are ideas to use Rust. Well, all these little tricks are getting way more complex in a more high-level language like C++, for example, or Python, because you don't have this kind of control, and it's tricky even in C. So yeah, C is the best option.
Okay, well,
for this kind of program.
Assembly would be the very best option, but that would be very, very hard.
Assembly, yeah, of course, yes. Assembly is always the best option, but
C is the next best one.
Yes, but you're gonna add so many bugs if we try to do this in assembly.
Yeah,
it's gonna be super inefficient because we won't be able to be as efficient as the C compiler. Anyway, okay. Read once, write once. We have those. We probably need also some. There's gonna be some SMP. Yes, these are additional memory barriers. Actually, let me go. Okay, we need barriers first. Do we have barriers? We don't, but we need that. So let me go back to Linux because how is this implemented? It's probably in compiler here. It's defined as memory barrier. That who knows what it is. Well, let's just, okay, let's go back here. Let's see how many errors we have, because in sched.c, I'm including, I'm not including list. Let's try to include list. And yeah.
Hey, that's not too bad.
Slowly, not too bad. Like we only have 1 million of errors. That's fine, yeah. But we're gonna make it, no problem.
Your machine didn't explode, so I take that as a good sign.
Yeah. What we have first? Let's see. List had declared.
That's
right.
just a warning.
Yeah, but we want to make it cool and clean, nice and clean. List head. Oh, because this one is, where is list head defined, right? We need some we need some types probably. So let's go back to Linux. ListH. ListH is defined as it's this one. Okay, we need that. FastOS list. We need to do a little bit of cut and paste here to import code, as you can see. We probably also need hListAdd. That because ListAdd also hList as hash list. And oh, look at that. We did those, I think. These three. FastOS list.h. So this one shouldn't complain anymore about these previous errors. What? Okay, wait, I'm compiling Linux. Like, what am I doing? Unknown type bool. Okay. We need also bool. We don't have type bools. So type def bool. Wait, int bool. Because type def is the opposite. And I think also Linux defines bool in types.h. Okay, bool is defined as bool. That will be defined somewhere else.
I always like that when you're looking for something and suddenly you realize it's defined as an alias to something else, and you have to find it something else.
It's okay.
Often it's somewhere completely different.
In our kernel, it will be defined as int. It doesn't matter.
It's good enough for us.
Okay.
Which means we can have 64 bits booleans. Woohoo!
Yes, exactly. List add valid unused parameter.
Unused parameter new. Yeah, well.
Okay. Let's see. Read once requires 2 arguments. Let me see. I had read once. How did we define read once?
You define that with 2.
Okay.
You copied that from write once, so that's why.
Yeah.
Hey,
wait.
Look at that.
Wait. Only these errors? Wow.
And those are warnings.
But
we need to fix the warnings and we're good.
Wait, we only have warnings? Seriously? I wasn't expecting that. This parameter entry. Okay, we don't have this, so I don't. SMP. There's no way that these are just warnings because we didn't implement these functions, right?
Yeah, that's what he said, implicit declaration.
Yeah, but then I was expecting the linker to. Oh, no, the linker didn't complain because they're in the dot, like they're defined. So if we would use those functions, the linker would complain that these don't exist.
But we don't actually use them, so
we don't use them for now. So that for now we're fine. Let me see. I would like to fix this line 64. Because debug list, we don't have debug list. So bye bye. We don't want debug list. Actually, you know what? Since this is going to be true all the time, this condition is never true, right?
Yeah, so we can get rid of that.
Bye and bye. And this one, same, because it's true. So we can just drop there. Goodbye, and we simplify the code. Make clean. Okay, yes, it's complaining that implicit declaration of. Actually, you know what? I have these functions, and we can copy from another project. Let me just find those, and we can fix it. Because I wanted to show you the barrier. There we go. Yes, this one. I found it. We can copy that from another project. List.a. Oops.
Copy paste driven development.
Yes, exactly. So that's what is called a hardware memory barrier. We're doing this, and this is like, so this memory barrier is a compiler memory barrier. It's like compiler don't do anything crazy to reorder instructions.
Okay.
This is a hardware memory barrier, is to say hardware, CPU, don't do anything crazy to reorder instructions, because also the CPU is doing some kind of reordering.
Okay.
So we have two levels of barriers. One in the compiler, and when we build the program, the compiler can decide to reorder instructions. And this one is a barrier in hardware, because once it's compiled, when we run, the CPU can decide to reorder instructions. So this one will be used to prevent the hardware from reordering. This one will be used to prevent the compiler from reordering.
Okay.
That's why we have this. And on top of this one, we have another copy-paste development.
Hey.
There
The
you
best
go.
kind.
SMP store release and SMP load, those that were required. As you can see, they are basically barrier. We could probably replace these with barriers, and that would work, but let's be fancy and correct and do that in the proper way. This is how Linux implement these functions. So I just copied them from Linux. It's not that but in Linux it's difficult to find them, because they're like, if this is defined then and that is not defined, then jump here and jump there. So these are just the missing pieces in our puzzle.
Yeah.
And make clean, make, look,
Woohoo!
no more. So we have lists.
We have lists.
And we just need to try to use them and see
Let's see if it works.
if it explodes or not. Let's do, I don't know, we can do like a static list. This is how we can define a list, declare actually a list in Linux. And I would create a task list.
Okay.
This is going to be like the list of tasks that I'm going to create. In each task, I was thinking I need to initialize the state, probably. That would be task running. Sorry, I just noticed this. It has nothing to do with the list, but I just noticed that. Let's see if just declaring that make everything to explode. No, cool.
Well, so it compiles. Does it run?
So now we can use Linux lists. Let's see if it runs.
Let's see if it runs.
Yes.
Woo!
But we, I was expecting that, because we didn't change anything in the code. We just added an empty list. All right, let's see. What we need to do now is to define. So I need to add when we create a task right here, for example, I need to list add task that wait, how did I call the next? Yes, the attribute that I'm using to point one task to the other is called next.
Next. Yeah.
Okay, I was remembering correctly. So task next, list add pointer to task next, task list. That means add this task to task list. And when I create a task, it will be added here with the state task sleeping. That is exactly what I feel like. This is the most productive evening I've had in a long time. Sorry.
Well, sorry, you and me both, because I didn't know anything about kernel programming when we started this series, and Yeah, and not only I did learn stuff about kernel, but also about C programming and
Yeah, and
assembly
now
and
it's amazing because Yannick is fixing me whenever I code. It's like, oh no, you need to do that.
well, just the standard C stuff.
Yeah, but kernel programming at the end is
Yeah,
really
yeah,
close to standards. It's way more standard than any standard because you don't have anything.
yeah.
So you need to re-implement everything based on your knowledge of standard. Okay, so when we create a task, it will be added here. And we need to remove a task from here when it will be executed. I guess it's time to work on a function that will be called schedule, maybe. Oh, another thing that we need, and I was thinking about that because I know how Linux works, and it's current. So we need a pointer to the current task.
Yeah.
This is going to be global, like I want to be able to access that from everywhere. So let's define that as a task struct current. Initially, it will be a pointer to init task. So this goes here. And this will always contain the currently running task. This is like initial kernel main thread, something like that. List of tasks waiting for the CPU. All right, that makes a little more sense now. And I was saying it's probably time to work on a schedule function, maybe.
Mm-hmm.
That is the most complicated part of today. Okay, so the schedule function in Linux is like this. No, oops. I fat fingered. Okay.
Fat figures, yeah.
What did I
I know
do?
the
Okay,
feeling.
that's cool. Void schedule void. It's like that. Because no argument, nothing. When a task wants to release the CPU, is just called schedule, and another task will be selected. At least this is what our kernel will do. It's not exactly that the semantic in Linux, but now our kernel, this is the semantic. Okay, what are we going to do? We probably need to have the concept of previous task and next task. So I'm gonna pre-allocate two variables for this. Prev and next. How about that?
Sounds nice.
Okay, previous task. I'm thinking. Let's say the current task because it's going to be the previous. The one that is running is definitely this guy right here.
Yeah.
At the beginning, especially, it will be init task.
Mm-hmm.
Then it will be something else. But the previous task in this scope right here will be for sure the current running task. The next one is going to be I would say the first item in the list, in TaskList, because it's not the last. The last is the one that we just added, because it's a FIFO list, first in, first out. So list first entry. This is defined in our list.h. List first entry. I don't remember what's the prototype. It's pointer type and member. Wait, there is a list first. I remember there was a list first entry. How do you check if null? List first entry or null? Okay. I remember correctly. There was another one. So this one, if the list is empty, because it could be empty.
Mm-hmm.
like
Yeah, if we haven't created any tasks
new
yet.
task, it could be empty. In that case, it should return null. That's what we want. So we want to use this one. The prototype is the same, pointer type and member. So, okay, I like this. Pointer type and member. So pointer is a task list. Type is going to be a task struct, and member is next. I think that's correct.
Okay.
What happens here? So if it's null, I like to do this. It's like Linux way of Linux coding style. Instead of doing next equal, I could have done this. But usually you find this way because it's more compact and the semantic is the same. So if not next, meaning that if next is null, what do I would need to do? I just need to return, because it means that there's no other task. Like the caller is saying, give the CPU to another task, but there's not another task. So I just return, right? Because let's see, or no, I was thinking, what if it returns the same task, but that's like the next task is the same as the previous?
That's because there's only one task scheduled. So
I would say that's not possible, and if it happens, is a bug, because if the current task shouldn't be in the we want to remove the task from the task list. So in Linux we would do something like a bug on next equal prev, and this would trigger a kernel panic. We don't have bug on.
No.
We could say define bug on X, and it's nothing. Yeah. So as soon as we implement bug on, this will be translated into an exception. And for now, it's just nothing. Okay, let's see if this compiles. Okay, we have errors. That's cool. Errors because I'm dumb and I didn't add the colon here. Make. Oh, okay. We don't have container off. That's something that we are missing also. Okay, container off in list.h. Container off is used here. So basically, container off means that we're passing a pointer to a structure, a type, and a member, and basically we're passing an item, an attribute of a struct, and it returns the entire object.
Okay.
That's let me find that, because I also have that, I'm sure. Actually, let's search that in Linux. Container off. There you go. Cool. Copy that.
So some people have bash script in their home folders or games. You have the sources for Linux. that's convenient. It's just sitting there in your home folder.
Yeah, it's convenient, right? Okay, we probably need also offset off. Oh no, okay, cool, fine. Now I recompile.
Compiling
perfect. It's working. Look, that's what we were missing.
Yeah.
It's complaining that prev is not used.
Yeah.
That's fine, but yeah, for now it's not used. Then we're gonna use it soon. Okay, what's next? Let's see. We need to depending on the so prev state. Let me think. we need to set like prev state as task sleeping. Because I'm expecting, I was thinking maybe I need to check if the current task state is running, but
Yeah.
should be run like, okay, I can do something like this, switch prev state. And because it's good to add some bug on
Some safeguards.
yes, exactly. So case task running. I could do if, but I prefer to use the switch case because I'm expecting to add more task states in the future. So
Okay.
I want to be able to catch all the all the possibilities. So the previous task should transition from running into sleeping, and it should be added to. So that's prev. It's funny because prev next, but prev is the previous task, and next is the attribute that points to the that is used to implement the linked list. So this will be added to TaskList. Actually, okay. Actually, this is interesting because I just introduced a logical bug. Because I'm always, this adds to the item to the top of the list. So I'm just creating starvation for everyone else. I need to list add tail, because if I
okay.
if I put to the top and add to the and remove from the top, then I put back in the top, the next one is going to be the same, and
Yeah.
so I'm
Okay.
bouncing the same task from the task list on the CPU. Instead, what I want to do it is to add to the tail. So I will get another one that will be added to the tail, and so on. All right. And everything else, so default, should be a bug on true, like always bug, because I'm not expecting a different state than task running. So let's do a return, even if this one should, the kernel should explode. So there's no really a return, but whatever.
Nothing to return. Yeah.
So the next task, let's do a similar, like this is going to be like update previously running task, and this one update next running task. Switch next state, and then we test it, and it needs to work like at first time because we're running out of time. Task sleeping would be the counterpart of this, right? So if it's task sleeping, do something. Default, it's another bug. I think that's correct. Okay, do something. Again, it's the opposite. The next task state, if it was sleeping, now it's going to become running. And instead of list add, there's going to be a list del. I'm going to do list del init because I'm clearing also the pointers just to be extra safe. Next, next. Yeah, that's an unfortunate naming, but it's not that bad. I mean, it's clear enough that this one is the task and this one is the attribute inside the task. Let me see, what else do we need to do? Okay, well, of course, we need to do the most important part, context switch.
Yes, because that's
this is easy.
Yeah, that's the
switch to
core
next
of this thing.
We were passing task structs, right? Yes, we're passing task structs. So cool. This becomes static because outside we are going to use only schedule.
Yes.
And in main, I'm not ready for this. We should be able to use that.
Okay, but
Let me
we
see.
need to initialize the.
Oh yes, we need to.
I guess.
We need to initialize. Sorry, what? We need to initialize
The list of running tasks, because
Yeah,
right now we don't have anything in our
yes.
tasks.
So at the beginning, it needs to be empty because there's only init.
Yeah.
When main calls TaskInit,
Yes.
if I remember correctly, we are adding.
Oh yeah. Okay.
So the
Yeah.
task list is theoretically is initialized.
I missed that. Yes.
Oh, that. So when the first guy, like when init calls schedule, let's see what happens. Let's simulate. It's getting the first item in task list. That is what we added here. And this is not, supposedly it's not null. It's not prev, even if this one will be just ignored for now.
Yes.
The state, prev state is running, right? Because we initialized
Yes.
task running. Perfect. Therefore, it's going to become sleeping. And we add to the task list. Okay, yeah. And then the next one becomes running, and we remove that from the task list.
Right.
That should work.
Yes. Ship it.
Ship it. Okay. Well, no, wait. Oh, because in sched.h
we need to
we need to export schedule.
Yes.
Not too much. Boy. Look, it's easier. Cool. Oh, come on. It compiled. Cool. First try. Can't believe that.
Yeah, I have faith.
Okay, it's doing something, but at least it's switching to task 1. So it's
it's a mono multitask.
Okay, there's a little bit of starvation, like only, but at least it didn't explode. That's not bad.
It didn't crash.
In main, let's see what we have. Okay, what if I want to try to do this, like I want to see if we switch from main to task 1. We should see only enload from main and enload from task 1, just to see if we have a reasonable context switch. Okay, we have a reasonable context switch.
So it's going back from task 1 to main.
It's from here. Wait, did I fix the error that, because if we add back to the top, we would select task 1 again. You know, the thing that I was saying before. No, but wait, no, that can't happen. Oh, wait, we are not updating current. We never update.
Of course.
The problem.
So current should be next.
I think it goes in next, right? It goes here. Current needs to be next.
Yeah, I agree with Danny. Ship it.
Ship it. Wait, did I fix the? Yes. Okay.
If it compiles, ship it.
Let's compile. So we ship it. Cool. Wait, it's.
We've got our first. We've got our first exception.
We got the first exception. Okay, wait. But
triple exception that reboots the.
Let's see if we make things worse and better. We're still doing the. Okay, we're still doing the first context switch.
Yeah.
And probably, if we go back here, we never get back here. Yes, exactly. Yeah. We never go back here. So the problem is the next switch from task 1 to main. And we know that the problem has to be in here, because the switch 2 is working, because we were relying on this one.
It was working 2 weeks ago, so there's no reason it's
exactly.
If the bug are okay, so
exactly. So the bug is right here. I'm wondering if let me see if there's a bug with this. Actually, no, there should. Okay, let's try. Maybe there's a bug in here. What if I do something like this? Like I want to see if for some reasons I'm re-adding the wrong task into the list. So this one shouldn't crash. At least it shouldn't trigger the exception, but it's triggering the exception. So that's not the problem. And I'm happy because that didn't make any sense. So that's fine. Okay, let's see. Prep current list.
That happened when you did set current to next, right? So if you remove that, maybe we'll see.
So maybe yes, it's something here. Current next state, prep state. Are we missing any break? No, I don't think so. So, okay, the problem here, again, is we implemented the scheduler because it was the next logical step to do. But what we would like to do, like I'm doing this because it's more entertaining. But what I would do offline would be to implement the proper exception handling and interrupt handling because I can debug. And I would like to implement also proper print K because I can, like, I would really love now to do like print K next print K prep to see what they are. We don't have that, so it's a little more challenging to do debugging in this way, but it's fine. It's it's just more entertaining.
But if you just remove or comment the current equals next, is it? I think that's the only thing you added that make it crash, right?
Yeah, this one is just
okay. So
on task
so
one.
why is this one crashing now?
So the thing is, why is it going over and over on task one? That's because, let's see what happens. Previous current next. So if I'm not updating current, when I go back from task one to init task, I should actually hit this condition here, because yes, because like prev is going to be current, and current is always pointing to init task because I never update that.
Yeah.
So that when I select again init task, I should hit this one. And but let's see what happens here. Oh, because I'm switching to the same. So next it will be equal to prev, I think. And a context switch will result in a function. Actually, it's like an op. Because next is the same as prev, and this is why I keep that there's always task one. So this one is needed because I need to update current.
Okay, so now it's in the second time it gets in there. It has
but
a problem.
I'm really curious to do like I was doing that before, right? Or next equal prev, and it didn't make any difference. Yeah. Oh, actually, it explodes. Spectacularly explodes. So wait. Could be that this thing. It could be that the compiler is taking initiatives and it's inlining this one, and I don't want this to be in line.
Come on, compiler.
I don't know. I don't know. This is like in line, no in line. Let's see. This is just hypothesis.
Yeah.
Because I don't see any problem here, but maybe whatever. Well, let's see.
Let's try.
Yay! It was the compiler. Dang it.
Oh, compiler. I am
Because
disappointed
if
in
you,
you, compiler.
yeah, because if you inline this one,
Yeah, then it.
it's messing up with the registers, and I
Uh-huh.
want to be a proper entry point, like where I'm pushing the registers and popping those. That I mean, I want to be a separate context because you see, I'm using register inside here. So if
Then
the compiler is inlining this chunk of code
yeah.
without saving the registers that I'm using here, I'm gonna mess up with the
Yeah.
existing registers that are used somewhere else. And yeah, this is why kernel programming at this low level is tricky, because you need to deal with compiler.
Yeah.
See
And he
the
says compiler sucks. Yeah, I
compiler.
agree. We should go back to editing
No, you know,
Xcode with the ultra edit or something, and type
yeah,
in bytes one by one. I agree, Danny.
yeah.
I will let you do that.
Compiler is doing its job. It's trying to optimize. And by the way, are we optimizing? Oh, in space. So I'm wondering if is it still working if I do like -03, for example. Let's see. Ooh, it's still working.
Ooh, it
Wow,
is.
our kernel is rock solid to drive
Yeah,
this like
Pasta
in
West
one shot.
rocks. Cool.
We're just crazy to do this in one
So
shot.
I'm curious now. What if we created a third task and see if
Oh,
that
that's
runs?
a good
Because
one.
we have a scheduler. Let's use it,
Hmm,
right?
that's a
Otherwise,
good
it
point.
yeah,
And
it
it's
doesn't.
actually, look at that. It's actually easy to uh wait. Where I okay, yes, yes. Now I was wondering, what if I can do this actually? Like, okay, this is just me with being extra paranoid to refactor. Entry equal task one wouldn't be better. So, and in TaskInit, I don't have to pass task one, because I can, I can do this. And
Okay.
but whatever. Let's not. Sorry, that's
one
refactoring.
one
You were
optimization at a time.
one optimization at a time. Okay, let's create task two. Task two. Oops, sorry. Task two. Hello from task two.
We've
And
got a question.
sure. Are these tasks the same as a process in Linux land semantically? Uh, okay, they are the same semantically as a kernel task or a kernel thread. Like if you do kthread create, these are the semantic of our kernel task is the same. In Linux, we also have user space tasks that are slightly different, even if the task struct is still the same. Like all the threads, user space or kernel space, they have their own task struct that is actually called task struct as we used. So from a certain point of view, yes, they are semantically the same, because in our land we don't have user space and we just have kernel space. In Linux, they're the same, except that they have extra properties, and some of them are like the fact that they are user space task versus kernel tasks, and stuff like that. But they're really close. We're really close to a Linux semantic. User space would be in ring 3, yes. In Intel, yes, and kernel space would be in ring 0. And if we continue this series of episodes where we're going to we would need to use something like that, like create a ring 3 where user space task will run and have a ring 0. So
I have
yeah.
no idea what that is, so I'm really interesting that when we reach episode 642, we're gonna talk about
Well,
ring
the rule
three.
is easy. It's like you can see that as a mode in the CPU. You just do a special jump, and then you can use only a certain subset of CPU instructions. And if
Okay.
you are in ring 0, you can use any instruction
Okay.
from the instruction. Look, Yannick, I created 3 tasks,
Yeah.
not 2, but 3. And then we do
3. So that's going to
task
be 4
init.
tasks in total.
4 tasks in total. Yes.
So you need to TaskInit T2 and T3, I guess.
Oh, you're right. Thank you. I didn't see that. Yes, I think that's. What if I would have done this? We would explode because the entry point would be null, and we would just see a reboot. So it
Let's
would be
not
really
do
hard
that.
to debug. Okay, let's do properly.
Yeah.
Let's see what we have. Make, ship it. Ooh, that's
Ooh.
123 main. I see also main.
I see main, yeah. Awesome.
Yeah, unfortunately, we don't have a sleep because we don't have interrupt. So,
No.
so we can't delay. Like we need to.
So if we had a proper scheduler, so something that would actually interrupt the process, we could then do priorities and stuff like that. Like have some tasks run more often than others.
Yeah, we can do priorities even now, like because the priorities depend they decide which task goes next, and it would determine the order in the list.
Okay.
So we could do priority right now. Obviously, in a fully preemptible kernel, priorities have a better meaning. That they're more enforced because we can interrupt any running task at any time. But like priorities in Linux, if you're running Ubuntu, if you're not running the low latency kernel, and probably you're not, you have this model right here. You have a voluntary preemption model. So tasks have priority, but you don't have a fully preemptible kernel. Okay, you're using tasks are interrupted. User space tasks are interrupted by the clock, but if you look at the kernel, purely at the kernel, tasks are never interrupted. And you have a scheduler with priorities.
All right. Okay. So another question from Danny. Well, question/remark.
I think at the moment we're using cooperative scheduling. Interesting. Well, it would be nice to implement the multi-core, multi-CPU SMP systems, but that's complicated. I don't know if we can get up to there. Like,
let's stay basic for now.
Yeah,
So,
yes. I mean there's so many things to show, like even with one CPU.
Yeah, we already have something that's really crazy because it can actually run 4 tasks. Well, as many tasks as we want.
As many as you
one
want,
after
like
the other. Round robin scheduling. Nice.
Yeah, and
that's awesome.
It's actually really deterministic. It's one of the most real-time systems, probably the most real-time system that you can ever find, because there's no interrupt, no paging, no page faults. And even if you run like one of those proprietary dedicated real-time system, they still have some they still have some interrupts or paging or so
right.
Yeah.
So that's cool. The only thing is that you can't rely on one task being run every X amount of milliseconds because
because we don't have the clock timer. But next episode, if we want, we can implement the clock and have a proper scheduler, like fully preemptible.
Okay, I will have a look at what the community team had in store last week. I think they did a stream where they asked us what we would want to see on the Ubuntu On Air channel, and some of those subjects can be offloaded to community streams. So I'm gonna have a talk with Monica, see what I can pick up, and so maybe the next episode might not be in 2 weeks, but there will definitely be a 4th installment of that. So
cool.
That's great. That's great progress. I like that. I like that because we go bits by bits, and so far I think I understood everything you did, So it's nice, and you're gonna
Oh,
put this code on GitHub, right?
yeah, I'm gonna commit and push so everyone can,
Okay.
and you can use this as a template if you're curious, if you want to experiment. Now
Yeah.
you have a skeleton of a scheduler that you can if you want, you can have priorities or do like I don't know,
Yeah.
other semantics or whatever, other types of scheduling policies.
Mm, awesome. So I do have a few questions
Sure.
now. Some that popped into my head spontaneously, and some that I gathered, by talking with different person online. So let's start with the first thing. You keep talking about kernel space and user space. How does those two things talk to each other, and what's what can something in the kernel space do that something in the user space can't do?
So usually what happens is as was mentioned but by Danny, the user space would run in what's so-called ring tree.
Yeah.
And okay, in Linux, there's the ring tree, so the user space, the user land can only use a certain subset of CPU instructions. If they try, like CLI or STI, the one that were used to disable interrupts and enable interrupts, user space can't use those, of course. But in ring tree, you can't use those, but you can do in ring zero. In addition to that, there's the whole paging and virtual address space and so on. So a user space process can only access a user space memory that is mapped in a certain range into each process address space. And the kernel has a different address space after the page isolation has been added. So everything was refactored and redesigned completely when there was the big mess about the side channel attacks. Because usually, but before, the kernel was mapped into all the user space process. So theoretically, that was done because the kernel, you could just switch to kernel mode, and it was just a jump, and the kernel would have access to the same virtual address space of the
Okay.
process without doing extra mapping. So that's how you can pass data from user space to kernel. At the end, you jump to the kernel, and that's just a mem copy.
Okay.
With page isolation, when you call the kernel with a system call, you jump into a different address space. And if you need to communicate between user space and address space, you need to physically remap some pages from kernel space to user space, and then do the mem copy. There's going to be a special mem copy that is checking if the addresses that you want to copy are in a certain memory range that is suitable for the main copy, like if the user space memory is mapped into the user space range, and if the kernel space memory is mapped into the kernel space range. And that's for big buffers. For small things, arguments of system calls are passed by registers, like we were doing with our kernel.
Okay, great. And so the second thing I wanted to ask is that if we forget about the difference in instructions, registers, and maybe segment addresses, would the same thing we did here for an x64 architecture would work if we could apply the same principle for an ARM architecture? For example, if we wanted to do a Raspberry Pi kernel, for example, of course, as I said, not the same instruction set, not the same segments maybe in memory, but the principles are the same, I guess.
It's the same. It doesn't change really much. If you think it changes, of course, in our kernel, it would change just the switch to function. That is the one that is using inline assembly. And I think we use some inline assembly in the barrier, the one that we added today in list, and boot.s the initial bootloader. If you replace boot.s with an equivalent boot.s in ARM, it's even easier than
Right.
Intel. And if you replace switch to, you can really add a couple of if defs and port PastOS into ARM like easily.
Ah,
And
nice.
boot PastOS in a Raspberry Pi, for example.
Cool. Cool.
Oh, and there's
So
also the console driver because it's using a port.
yeah, maybe different address and something. So that's cool because we could have then that microkernel thing be very specific for one task, and we could load that on a Raspberry Pi, and it would probably be a lot more efficient than having a whole operating system and just in boot time
Boot
for
time
starters,
is like super
and
fast.
and then the operating system probably does lots of stuff in the background, which is time that you're not spending running your program. So I don't know. I'm thinking some kind of LED driver, for I have a friend who
Of course,
has
something
a
simple.
Raspberry Pi. He uses a Raspberry Pi to drive his house lights for Christmas, and so instead of having a full OS, which probably isn't used at more than 10% of what it can do,
Exactly. You don't
have
need
a
a
very
full
specific driver.
Linux installation to like drive a few lights and so on.
Right, so that's nice. All right, so I think it's been an hour and a half, our usual running time for this series apparently. So I suggest we stop here unless you have anything else you want to show tonight.
I think we have we did the schedule.
Right.
It's more than enough.
Yeah,
There's a Isgramor. Hello. And Danny was saying something else about Windows has bits in the kernel system libraries permanently mapped. I think it was called the TEB. Okay, I'm not familiar with that. But I know that Windows has some permanently mapped memory. And same for Linux. So it used to have like remember the thread environment block. Oh, yeah, I'm not familiar with that, but it makes sense. It's like the kernel as it was before the page isolation. Like everything was mapped into all the user space processes for speed reasons, for performance reasons.
And yes, Isgamor, you arrived just when we finished. But
you can check out
the VOD. The VOD will be available on YouTube, so watch that if you're interested. And remember that there are 2 other episodes of that. This is part 3, so I strongly suggest starting with part 1 if you haven't watched that, because every episode is a continuation of what we did previously. So it will help. Right. Thank you again, Andrea, for joining me and showing us how to do some kernel magic.
Thank you, Yannick.
And so I will be back in 2 weeks. Don't know yet exactly what the subject will be. Maybe part 4, maybe something else. I will have to have a chat with Monica about that. Thank you, everyone on YouTube and Twitch for joining us. Fun for chatting with us in the chat for those services. And well, I guess have a good end of day, evening, whatever it is, wherever you are. And I will see you in 2 weeks. Bye bye, and good night, Andrea.
Bye bye.